Hello everyone, my name is Barbara and I would like to welcome you to our latest Knowledge webinar episode. This is number 200, yay, celebration. This week, PTC Mathcad to optimize engineering productivity. This webinar will provide an overview of PTC Mathcad and how the software enables calculations and engineering design within an environment that is specially tailored to the needs of engineers. Topics covered will include the numeric and symbolic math engines, units management, creating functions, interacting with Excel, plotting, solving and optimization, templates, among other things. So don't go anywhere. Today's presenter, Anji Seberino, there she is a principal application engineer at PTC. She is a technical specialist for Mathcad, and in this role, Angie works to educate engineers and organizations on the capabilities and value of Mathcad so that it can be incorporated into their design and analysis process to optimize engineering productivity. And she'll show you exactly something like that today. But before, let me tell you a little bit about Novage. Novage is one of the largest online stores for design software. We offer a huge assortment of software solutions that cater to virtually every designer's needs. You can visit us at novage.com and see, all our products. And for more daily software news and limited time promotions, pay a visit to the Novage blog and follow us on Facebook, Google+, or Twitter. Coming up next week, CFD and FEM simulation on the cloud. Last but not least, today's webinar is free and is being recorded live. So if you want to rewatch this or any webinar episode in our collections, just head on over to Novage's YouTube and Vimeo channels. And now I'm going to share Angie's screen so she can take over. There you go, Angie.
Thank you.
Great.
Okay. Good morning and good afternoon, everyone. This is Anji Seberino speaking. Thank you for that introduction, Barbara. And thank you all for joining today. So I'm going to spend the next 45 minutes or so taking you through the Mathcad application so that you can have a solid understanding of what Mathcad is, how it works, the capabilities that it provides for engineers, so that engineers can do their work in an environment that is more natural and easier to use than other methods of doing engineering calculations. So we're just going to spend a moment going over a quick overview of Mathcad so that you know what the application is all about. Then we're going to go through a live product demonstration, and most of the time today will be spent in the product, doing live, hands-on work in the product. I'm also going to show some examples, some industry examples of how people have used Mathcad to create complete engineering documents, and then we'll open it up to Q&A. So before we go into the product live, I want to just get everybody on the same page as far as what Mathcad is. Mathcad is essentially and fundamentally engineering calculation software. It's been around for a very long time, about 30 years now, and it was designed specifically and exclusively for engineers. And it spans all disciplines of engineering, so electrical engineers, mechanical engineers, civil engineers, structural, chemical, physicists. They all use Mathcad. So it's a very broad application across all engineering disciplines, and it's also a very deep application as far as mathematical functionality goes. So if you want to dive into some very advanced math exploration on the electrical side, you can do that, or on the mechanical side, you can do that. So it spans all disciplines of engineers, and it's a comprehensive application. So when you're working with Mathcad, creating engineering documents, you're combining live math equations and results, live math content, with text and graphics. So you're creating this rich document, this rich engineering document that has a live math engine running behind it. So it might look like a Word document, but it has a math engine running behind it. So as you make changes to design variables, input variables, analysis parameters, those changes will propagate forward and update each and every dependency that follows. Okay, so at the end of the day, you have this engineering document that can be reused, it can be shared, it can be published, but it's also a live math engine. It has two types of math engines, a symbolic math engine and a numeric math engine, so we're going to take a look at those. And one of the distinguishing factors about Mathcad is that it manages units. So it handles your engineering units for you. And we'll go into a little bit more detail on what that means as well. And so when you do your work in Mathcad, when you're done, you have this readable document. All right, so let's go ahead and go into the product. So give me just a moment here, and you will see your screen update. Okay, so here we go. And when you initially open Mathcad from your start menu, so this is a Windows application, and when you initially open Mathcad and you create a new file, you're going to essentially have a blank document. Okay, so this is a blank document. Of course, you can open an existing file and reuse it, but what I did was just create a blank document, and it just has some header information here at the top, and that's pretty much it. So there's a live math engine that's running behind the scenes. Okay, so I'm going to type in, what I'm going to do here is type in some math expression, a very basic math expression. And just to show you how this math engine works, 678 plus 9876 divided by the square root of 33, we can type equals, and there's the answer. Okay, and now there's a lot more we can do with this, but just to show you that the math engine is running, it's running behind the scenes. Now we're going to come back to this. What I'm going to do is jump over to a completed document that was created by NASA and show it to you. Then we're going to come back to this and go over some of the building blocks and components that were used to create that document, just so that you can visualize what the end result would look like when you do something in Mathcad. So this is a Mathcad document that was created by NASA, and this was essentially a study that was done to determine if surface acoustic wave devices would be adequate on vehicles for monitoring. You know, could they monitor vehicles with SAW devices, SAW device technology, instead of whatever they were using, and would that be effective? So this is really a study on surface acoustic wave devices and the feasibility of that. So this is just the front page. I'm going to scroll down. I'm going to scroll down here. And what you're seeing is a comprehensive document that has integrated the text, the documentation, with the math. So in Mathcad, we don't have a separate area for our math and then a separate area for our text. It's all integrated together into a readable final document. And so you can see here they've written some introduction, some background. They've put in a bitmap diagram here of the device. They put in a diagram of the circuit. And so as we go down, now this, again, this is in Mathcad. If you look at my application, we're in Mathcad here. We're not in any other application. When we go down, we can see some of the math. So these are all variable inputs. Okay, so the synchronous frequency set to 52.6 megahertz, the substrate type, the bandwidth, and the delay in the wavelength. So when we define input variables, we define them with units, and I'm going to talk some more about that too. But we define them with units. So F naught is not 52 by itself, it's 52 megahertz. And that megahertz unit will be used in the equations and in the formulas and the plots that follow. So if we scroll down a little bit more, we can see some more inputs on the material properties side. The acoustic velocity in meters per second, the piezoelectric coefficient, the capacitance. As we scroll down, we can see some calculations that use those input variables. The wavelength, lambda, okay, and that's equal to 60 micrometers. So micrometers is being calculated according to the units on velocity and F naught, okay, the width of the electrode. And let's continue to scroll down. These are basic calculations. Here things get a little bit more advanced. Okay, so here's the formula to calculate the aperture, and then the frequency response equation. Okay, so X as a function of frequency, and then H is defining the frequency response. And as we continue to scroll down, we have the conductance, the susceptance. So these are all just standard formulas and equations that they're using. And then we finally have the plot. Okay, so we're plotting frequency on the x-axis. We're basically plotting the frequency response. Frequency is on the x-axis and the response is on the y-axis. Okay, so that's the plot. Now this is all live math. So if we were to go back up to the very top of this document and change any of these inputs, if we were to change the synchronous frequency to 80 megahertz and this acoustic velocity to something else, I'll just say 55, and hit enter, everything updates. So as we scroll down, we're going to see a new wavelength. We're going to see new results on the frequency response, on the susceptance. Let's go down to the plot. And you can see that the plot has updated. Okay, so that's the idea. That's how Mathcad works. Whenever you make a change to any kind of variable or input or formula or equation, everything updates automatically. And so immediately you can see the effect of your changes to inputs on your desired results, your desired outputs. So there's the updated plot. Okay, so I just wanted to show that to you so that you can visualize what a completed document looks like and how it works. So now let's go back over here to our document. We have this basic calculation. Now one of the things that Mathcad does, and you notice this in the NASA document, one of the things that Mathcad does is represent all math equations, all of your math content in natural math notation, no matter what it is. So here if we have a definite integral and we type the sign of t squared times 17t dt, and we integrate that from 0 to pi, we're going to see the integral. We're going to see the exponent notation. There's no confusion over what the equation is. This is just like we would see it in a textbook. It's just like we would see it in works formulas or any kind of mechanical engineering reference. This is exactly how we learned to document and write down our engineering equations. Now what we want to do is assign this to a variable. So maybe we're calculating some kind of volume or fluid flow through a pipe or power dissipation across a component, whatever it is. We're going to assign it to a meaningful variable, and then we can use that variable in a subsequent calculation, and we can assign that to a variable. And so we'll just call that vol2, and then we build on, so on and so forth. So now if we want to provide an input variable into our integral, we're going to define an input n, initialize it to 5. So this is an input now, and so maybe I'll just highlight that. So that's an input, and we're going to raise t to the nth power instead of the second power, raise it to the nth power. And now that value of n gets substituted into the definite integral, and volume updates, volume 2 updates. Everything will update. Okay, so now we can say, what if n is equal to 3? Everything updates. Now, the numerical results, just so that everyone's aware, can be formatted. So we can change, we can control how many decimal points of display precision we want to see there, whether we want to see this in engineering notation, scientific notation, you know, whatever we want to do, we can change that there. And this numerical result, the formatting there we can also control how many decimal places we want to show. Okay, so these are the decimal places. Now this is a numerical result. Okay, that's a numerical result. The math engine also has a symbolics component. So we can take that same definite integral. Let's take that same definite integral, and this is where things get very powerful when it comes to the design side of things. Let's take that definite integral, and what we're going to do is, instead of integrating, let's just type the sine of x, we'll integrate the sine of x times the cosine of x dx. And instead of integrating from 0 to pi, we're going to integrate from a to b. Okay? And now we can't get a numerical result because we don't have any hard-coded limits on the interval. So we're going to use the symbolics engine to ask for a symbolic solution. And so to do that, we click on the symbolics. We're going to click on the arrow there. And now Mathcad is going to give us a symbolic solution. Okay, so it's going to give us an answer in terms of the limits. And the first time you execute the symbolics engine, it takes about 3 seconds or so. And now here, we can see the solution. And now what's really neat is we can take that symbolic solution and we can assign it to a function of the limits a and b. Okay, so maybe we're calculating some fluid flow through a pipe, and a and b are starting and end points. So we're going to define a function and of the limits, and then we can evaluate that function numerically. So at 3 and 8. Okay, so that is a very quick overview of the numerical engine and the symbolics engine. So let's talk about units. The math engine in Mathcad is units intelligent. Okay, and this is incredibly important. It's units intelligent, and that means that it's going to do 3 things. That really boils down to 3 things. It means that Mathcad is going to take care of all of your unit conversions. It's going to perform all of your conversions. It's going to carry units through calculations. And it's going to flag errors. It's going to tell you if you have a units-related error in one of your engineering calculations. Okay, so we're going to go over here to the units button, and if we click on this, we can see all of the units that come with Mathcad that are installed with the Mathcad Units library. Now this list is organized in alphabetical order, so you can see the different unit dimensions listed here, and then we can scroll through this and you can see the itemized units under each dimension. So if we go down to capacitance for the electrical engineers, you can see farads, nanofarads, picofarads, microfarads, current, also another one for the electrical engineers, energy. If we go down to force for the structural engineers, you can see a lot of different units for force. Kips, newtons, kilonewtons, meganewtons, pound force, ton force. And as we continue to scroll down, you can see for length, we have quite a few units for length, which we'll work with those a little bit here in a minute. And so as we continue to scroll down, you can see that we have hundreds of units that are built into Mathcad. Here are units of pressure, PSI, and temperature units as well. So in Mathcad, you can convert readily between Fahrenheit, Celsius, Kelvin, Rankine, okay, units of time, units of torque, velocity. So when we're working in Mathcad and we want to use units, we're simply going to add units to our term. So let's just consider a basic example here. So we're going to say 44 feet, okay, plus 8.5 yards, plus 320 inches, plus 67.2 millimeters. Maybe I should add a couple of zeros to that one. Okay, so Now here we are, and we're going to hit equals, and we're going to get an answer with units. Now, we're working in the SI unit system. You decide what unit system you want to work in. So you can see my unit system is set to the SI system, but if you'd rather work in the US customary system or the CGS system, then you can switch your unit system here. We're working in the SI system. That means that Mathcad is going to give us an answer in SI units. And whatever the base unit is for SI is what is going to be provided in our answer. So the base unit for length in SI is meters. So when we hit equals, let's hit equals right now, the answer is in meters. Okay, so there it is. Meters is the default base unit for length in SI. Okay, so now the beauty of this is that we're not confined to using only SI units. As you can see, we've used feet, we've used yards, we've used inches. We can use any unit we like, but our answer will be in SI. And B, we can convert this unit to a different unit. So if we don't want meters, then we just type in the name of the unit that we want. So suppose we want to see this in inches. We type in inches, and Mathcad will convert the answer to inches for us. And remember, if you don't like this display, then you just go up here to Math Formatting, and you can change that pretty easily. Okay, so now there's the answer in inches. Suppose we're working with a couple of different engineers, and one is overseas and one is here, and they're using, one is using US customary units, the other one is using SI units. So we can display this in multiple units. So let's display this length equals meters, and then we can also display it in feet or inches or whatever the unit is that we want to display it in. And so in Mathcad, you'll never type in a unit conversion factor. You'll never type in a multiplier, because all of these unit multipliers and conversions are built into the math engine, and they're extremely precise. All of the conversions and all of the calculations in Mathcad are done with 64 bits of floating point precision, according to IEEE's definition of 64-bit floating point arithmetic. So everything is extremely precise. There's not going to be any round-off error. There's not going to be any rounding errors. You can certainly round in your display, but the calculation itself is going to always be done with the full 64 bits. So let's suppose we have units of different dimensions. Let's define a variable, mass, 8 kilograms, and let's just define acceleration and set that to 6 meters per second squared. And now let's multiply mass times acceleration and type equals 48 newtons. We're going to assign that to a variable called force. And now we can see that Mathcad knows what the relationship is between kilograms and meters per second squared. When you multiply them, you get a unit of force. It knows how to simplify those units into the most simple base unit of the Newton. Okay, we can consider another example. Let's consider, well, let's take a look what happens when we try to work on incompatible units. Let's take 5.5 seconds and try to add to that 99 yards, which we know we can't do. And so it tells us we have an error. And so this is nice because in other applications, in other tools, you're always going to get an answer here, but it won't be right. It'll be 5.5 plus 99. But Mathcad alerts you so that as the engineer, you have to fix this before this mistake can propagate forward into the rest of the design. Okay, so we're catching engineering errors up front instead of later on down the road. So that's a quick crash course on units. The math engine, let's move on because there's quite a bit more we want to go over. So the math engine operates on scalars, it operates on vectors, and it operates on arrays. Okay, so let's create a couple of vectors here. I'm going to go to the next page. Let's go to the next page here. Okay, and let's create a force vector and let's create an area vector. And we'll do a structural engineering calculation. So force, and now we're just going to go up here. Now there are multiple ways to create these vectors. You can create these by hand, like I'm doing here. You can import this data from Excel, so you don't have to type in these numbers. You can copy and paste information into these vectors, okay? And you can programmatically read data in, read file function, read data function, read Excel function. So there's lots of ways to get your data into Mathcad if you don't want to, certainly don't want to type it in. So there's our forest vector. Let's create an area vector. And we're going to create a vector, 4x1 vector. Okay, and so now here we'll just say everything's going to have units of square inches on this one. So what you're looking at here is the addition of units to the entire vector at once. That means that every element in that vector is going to take on the units of kips, in the case of forest, and the units of square inches. So now let's calculate stress. So we're just going to say forest divided by area equals, and we get a vector of output. So the math engine operates on scalars, it operates on vectors, and matrices. Now we're going to assign this to a variable called sigma. And Pascals is the default for pressure in SI, but we don't want Pascal, so we're going to change that to units of KSI, kips per square inch. Okay, and there's our unit conversion. And now we're going to plot this data. Okay, so let's create a 2D plot, and let's plot force on the x-axis and sigma on the y-axis. So we're just going to go up here to the plots. We're going to insert a 2D plot. And on the x-axis, we're going to plot our input variable force. And here, we can put in the units that we want to scale the x-axis to. So we want to scale this to units of kips. That's the unit we're working with. On the y-axis, we're going to plot sigma, and we want to scale that to units of KSI. And then we'll see our plot, and there it is. Okay, and let's just make it a little bit bigger. Okay, so there's our plot. So now we have this plot, and there's all sorts of things that we can do with it. Obviously, the first thing that we probably want to do is control what our line looks like. Do we want it to be a solid line, a dashed line? How thick do we want it to be? What color? So all of that can be done up here on the ribbon. But more importantly, what if we want to add another curve, another data set to this plot? Let's say we have another stress curve. So we're going to click on the y-axis, and we're going to click on Add Trace or Add Curve. And now here, let's scale. We don't have another data set, so let's just scale this data set by a factor of 2. We'll just multiply it by 2. And we also want to plot KSI for that. And then we hit Enter. Okay, and now we have another stress curve. So we have our initial nominal stress curve, and we have our scaled stress curve. And then we can customize that line as well. And then the next thing we're going to do is we're going to add markers to this plot. So we can add vertical markers, we can add horizontal markers. So if we add a vertical marker, we can then, it'll automatically go at the maximum value, and we can drag this marker across the plot to extract the value on the x-axis. So if we wanted to pull out that peak there on force for both of them, then we can look at that marker there, that call out, and it tells us that force value is 765. Okay, now what we can do next is establish a threshold. So if we have a max stress, let's say we have a max stress at exactly 25, okay, we are going to add a horizontal marker, and instead of moving this line manually, I'm going to type in max stress. Now this is really nice, because when I hit Enter, that line will automatically move to the max stress requirements. I'm going to hit Enter right now. Okay, and you can see this threshold has positioned itself at exactly 25 KSI. And now we can move this vertical line for force, and we can extract the exact values where we hit that threshold. Okay, so if we have a project manager or some kind of requirement for our max stress or min stress, whatever the requirements are, we can define them in variables and then control the position of the markers in the plot according to those thresholds. Okay, so that's a little bit about 2D plotting. So the next thing I want to go over real quick, and then I'm going to show some examples, is the interface with Excel. So Mathcad, I'm going to say using Mathcad and Excel together. Mathcad and Excel work very well together. Okay, so the integration between Mathcad and Excel is quite seamless, and it's very easy to exchange data between the two applications. And so typically what people want to do is import data from Excel and then use Mathcad's math engine to interpolate that data, maybe fit that data to a curve. That's some of the more advanced math functionality, regression, maybe plot the data, add units to the data, and then process the data with units, because they can't do that in Excel, but they can do it in Mathcad. So there's a lot of ways to bring Mathcad data into Mathcad from Excel. Okay, and so I'm just going to highlight two of those methods. One is using the data import wizard, and the second is using the Excel component. Okay, and then the third method, I'll just say the read file functions. Okay, that's more programmatic. So the data import wizard, if we just go over to the input output tab over here, there's a read Excel button. Okay, and so we can click on that, and then we browse for our file. It brings up this wizard, and we just need to browse for our file. So I have some data here, TVA, and this is very simple data. It's time, velocity, acceleration, 3 columns, 10 rows. I'm going to click on Insert. Okay, it puts the read Excel function in for us, and it gives us the range. It's coming from sheet 1, A1 to C10. Now we're going to assign that to variable code data. And now we can look at our data. Okay, and there it is, 3 columns of data, time, velocity, and acceleration. Now that we have that data in Mathcad, we can do what we did before with our force and area vectors. We can calculate distance. We can do interpolation. What if we want to know what the acceleration is at 1.5 seconds, at 1.8 seconds? We're going to call an interpolation function to interpolate. We can plot this data. But most importantly, the first thing that we would do is we would create a time vector with units of seconds. We would create a velocity vector with units of kilometers per second, an acceleration vector with units of kilometers per second squared, because then we can leverage the units intelligence in Mathcad and work with units in everything that we do. So that's one way. Now this is linked to Excel. Okay, this is linked to Excel. So when that Excel file changes, this will always update. This will always update, okay? It always updates when the Excel updates, okay? It's always linked. So the second method is using the Excel component, okay? And this one's a little bit different. The Excel component will actually let you embed an instance of Excel inside of Mathcad. So if we click on Excel component and click on Insert, we're going to put an Excel object inside our Mathcad file. So here it is, and you can see it's blank, it's empty. There's a section at the top for inputs. There's a section at the bottom for outputs. So inputs, those are inputs from Mathcad to Excel. Okay? So any data we want to send from Mathcad to Excel, and then in the bottom half here, outputs, this is data we want to read from Excel to Mathcad. And this is actually quite slick the way it works. What happens is when we double click on this object, it's going to activate Excel out of process. So let's double click on this. And there's Excel. And anything that we do here, anything at all, let's just type in some numbers. There we are. Okay? And let's close this. Anything we do there gets inherited into the Mathcad document. So now we have that here in Mathcad. Okay, so what we can do is we can say, well, we have some information in Mathcad. I think we had a variable called, we had max stress, or max stress. Max stress equals 25. So let's send that in. Okay, so we're going to say into into this Excel object, and we don't want to do A1. Let's go to F5, just to make sure we're writing into something that's not already occupied. Into F5, let's send in our variable max stress. We hit enter, and that's going to go right into the spreadsheet in location F5. Now, as we activate this, let's do a calculation here and store it in F6. Let's say this is going to be F5 multiplied by 0.33. Okay, 8.25. And let's say that this is something that this is a critical output that we want to read out back to our Mathcad document. So we'll just highlight it. We'll make it bigger. Let's close this. So that's an F6. Okay. So now coming out of Excel, let's read that value out. So coming out of Excel, this is our updated thresh, and that's going to come out of F5. So from this Excel object, subscript F5. We need quotes there, F5. Okay. And then down below the object, we're going to type updated thresh equals. Now watch what happens. Oh, F6. F6. Okay. So now watch what happens. We're going to go up here, this requirement, max stress, we're going to change it. Okay, so let's just say that that's a requirement. So instead of 25, let's change it to 75. And our updated threshold coming out of Excel updates to 24.75. Okay, so that's how that works. It's very, very fluid. So we change our input variable here in Mathcad. It goes into Excel. Excel does its thing, whatever it is. Maybe it's sorting data. Maybe it's filtering data. Maybe it's doing a pivot table and providing the pivot point out. Whatever it is, we're going to read out and read in back into Mathcad and then keep going. Okay? And the nice thing about this is we don't have to activate Excel. We set this up one time. Okay, now I can change max stress all day. There it is, 65. Hit enter, my updated thresh updates. Okay, I'm never activating Excel. I'm never going into Excel. Excel is still running, but I don't have to launch Excel. I don't have to activate it. I don't have to work inside of it. I can just change my input to Excel here. That input goes right into Excel, and Excel spits out my new answer. And then we can also hide, if you want, just as an FYI, you can hide those as well, resize this, control the display a little bit. Okay, so two ways to integrate with Excel, dynamically or using the Excel component. All right, so let's see here. We talked about the numeric engine, the symbolic engine. We talked about units. We talked about scalars, vectors, matrices, Excel, plotting. So let's take a moment to talk about templates. Everything that you can do in Mathcad, everything you do as you're creating these documents can be created into a reusable template. So if you're working across a project, across a team of people, or even as an individual and you want to reuse something you've already done, and maybe you have some headers and some fonts that you prefer that you've established on your document, your margins, you can see I have a header here. Whatever your preferences are basically for your document, you can put into a template, but you can also put math content into a template. So if you have an engineering design and you want to reuse that and only have somebody change the inputs and then have everything else be all done for them, automatic, all the plots, everything's done, create a template out of it. And when you create a new document from a template, just go up here to the M prime, and click on New, and then select New from Template, and then you can select the template that you want. So if I wanted to do, let's see here, any one of these, main analysis, it's going to create a new document. I don't have a data file, but it's going to create a new document with all of the math, all of the plots, all of the structure, everything's going to be there. Now, maybe I should do a different one. So if I open a new template from, let's see here, I did my templates. Let's do my template, shared templates. Oh, which one do I want to do? I guess I could do any one of these. This one. Okay, so it inherits, this is the one I'm using today. It inherits my header. It inherits all of my math preferences, you know, how many decimal places I want. It inherits my font preferences, all of that stuff. So that's how templates work. So templates will eliminate a lot of rework. You can reuse designs, reuse analysis documents, and just change the inputs, just change the data files. All right, so let's look at some examples. So the first example I'm going to show is a structural engineering example, and this is a beam deflection analysis created in Mathcad. Okay, so let's just go past the cover page here. All right, so here are the inputs. We have the base, 10 centimeters. We have D, 15 centimeters. We have the moment of inertia. That's a calculation, and the units are centimeters to the fourth power. Now we're going to select a material, okay, a material for this beam. And we're reading in the material data from Excel. Remember that read Excel function? We already went over that. So that's the read Excel function. We're reading in this Excel file, and we're storing the modulus of elasticity in a variable called eData, okay? And so now, depending on the material we want, we're going to set the modulus and gigapascals. Now we have more inputs. The length of the beam, 15 meters. The load, 500 newtons, and the load position is at 11 meters. So 11 meters into the beam, if a 500 Newton load is placed there at 11 meters on a 15-meter beam, let's do the analysis of the beam. What's the deflection? What's the shear? What's the moment? Let's figure out what all of those things are. So let's scroll down. Okay, here are the calculations. Okay, these are the force balance calculations for the left and right hand points. And so these are standard equations out of Rourke's formulas. This is the function for shear. Shear as a function of position x. This is the equation for moment. Moment as a function of position x. Remember, position, we're at 11 meters. And the deflection equation, okay, as a function of position. So now we can actually calculate the deflection halfway across the beam. L over 2. L over 2, because we have a 15-meter beam, should put us right at 7.5 meters, and it does. And the deflection at 7.5 meters is negative 13.12 millimeters. Okay, so halfway across the beam, we know we have negative 13.12 millimeters of deflection. So now we do some more calculations. The deflection at the load position. Okay, A is the load position. So there we're deflecting by 2.39 millimeters. The distance of maximum deflection, where are we deflecting the most, and the actual maximum deflection. Then we can create the plots. Okay, this first plot is a plot of the shear in meters versus newtons. The second plot plots the moment. And the last plot is the plot of deflection. So this is a summary table, and then we have the deflection plot. Okay, and these are markers. So we've marked the position of maximum deflection. We've also, well, actually, I think we've, yeah, and we've also marked the load position 11 meters. Okay, so that's what this marker is on the right. Okay, so this could be made into a template. So you install it as a template, and then any engineer, you, your colleagues, any other engineer can come in. They can get this template. They can change the material of the beam, change the load, change the length of the beam, change the load position, and that's it. And then they're going to have the whole deflection analysis already done, already complete with the plots, everything will be done for them. So within 5 seconds, 10 seconds, or 30 seconds, however long it takes them to set the updated length of the beam and the load information, maybe 30 seconds, then the deflection analysis will be done because it'll be run as a template. So then the next section of this, there's the contour plot, actually has something called a Salwa. So So in Mathcad, we can ask Mathcad to solve for our input values that satisfy our desired output values or our design constraints. So here, we're asking Mathcad to tell us what the minimum moment of inertia is required such that a 500 Newton load does not deflect by more than 3 millimeters. Okay, so if we can write that problem down mathematically, Mathcad will give us the answer. It'll tell us what the minimum moment of inertia is. So this is an optimization problem. We're trying to optimize or maximize or minimize an output of a function. In this case, we want to minimize the moment of inertia. Okay, so that's why we see this function minimized, because that's a built-in function to Mathcad. This is an optimization problem. And Mathcad tells us the minimum moment of inertia is 1.08 times 10 to the minus 4 meters to the 4th power. We could certainly change that to centimeters to the 4th power as well. So we'll just put a C in front of it. Now it's in centimeters to the 4th power. And so here's the requirement. Deflection as a function of moment of inertia must be greater than 3 millimeters. Negative 3. We don't want more than 3 millimeters of deflection. We can change that and we'll get a new moment of inertia. So scrolling down, the next solve block says now calculate the minimum dimensions if using a beam with a rectangular cross section. Okay, so here are requirements. The moment of inertia has to be less than 1/12 times the base times height cubed. But more importantly, our second requirement is our base has to be greater than 1/5 the height. Okay, so we know that much. Now we're going to ask Mathcad to give us the minimum dimensions of the beam. And it comes back, again minimized, and it tells us the minimum dimensions have to be 5.88 and 29.42 centimeters to satisfy these requirements here. Okay, so that's the beam analysis example, but it does a nice job to show how all the pieces come together to solve a real-world engineering problem in the structural engineering space. So the next example, I'm going to show one, maybe two more at the most, and then we'll open it up to Q&A. So the next example is on the mechanical side, and this is quite a nice mechanical engineering example. And what this does is calculate the critical speed of a shaft bearing, okay, for different diameters, different outer diameters and inner diameters of this part. Okay, so the Young's modulus here is initialized to 210 gigapascals. We're going to use that. You can see everything is being done with units. So now here we have some scalar values defined as inputs. The outer diameter, the inner diameter, and the mass, 12 centimeters, 9 centimeters, and 10 kilograms. And then we're going to do some initial calculations. So this is a simple analysis. We're going to calculate the second moment of area. Then we're going to calculate the stiffness coefficient. And finally, we can calculate the critical speed of the shaft in radians per second. But what we're going to do next is very powerful. We're going to iterate over multiple outer diameters and multiple inner diameters and calculate the critical speed for every combination. So not just the matching pairs, but each and every combination. Okay, so let's scroll down. And I didn't go over this in what we did earlier, so I'll go over it now. But basically, this is our input table of test cases. And that's on the matrices table, and it's just inserting a table here. And this is these are two columns. The left column is a vector called D with units of centimeters, and it's going to iterate the outer diameter going from 13 centimeters down to 10 centimeters. The second column is for the inner diameter, and that goes from 6 centimeters up to 9 centimeters. So for each and every combination of diameters for the shaft, calculate the speed, the critical shaft speed. And in addition to that, we're going to add a requirements validation. Okay, we're going to set our threshold RMIN to 22,000 RPM. Now, to iterate, we write a for loop, a nested for loop. First, we're going to loop over. This is a Mathcad program, so you can program in Mathcad as well. First, we're going to loop over the outer diameters. Then we're going to loop over the inner diameters. And for each combination, we're going to calculate the moment of inertia, the stiffness coefficient, and the critical shaft speed. And we're going to check if it meets our requirements or not. Okay, that's this here. If our critical shaft speed is greater than 22,000 RPMs, we pass. Otherwise, we fail. And then we're going to return 2 arrays out of this program. One array for the speeds and 1 array for pass-fail results. So we're going to get 16 outputs instead of 1 output because we have 16 combinations here for the shaft. So these are the results. The one on the left is the shaft speeds in RPMs. The one on the right is the pass-fail results. And those don't mean a whole lot without labels. So then we just add some labels to those, and I'll show you what that looks like. Okay, so now here we can see the shaft speeds with labels for the diameters on the rows and columns, and the pass-fail table below. So we can look down here in the lower right corner and see that we fail, and then we can look and see, oh, we fail when the outer diameter is 0.1 meters and the inner diameter is 0.09 meters. But up here in the upper left, we pass. Okay, and then we can look at what combination of diameters allows us to pass. So this is a very, very nice example because it iterates. It iterates over a sequence of inputs and considers every combination and does a pass-fail analysis according to a requirements validation, and then gives you a nice table of summary results. Okay, so that's a mechanical engineering example. And then on the electrical side, I'll just go, the NASA example was definitely had an electrical focus. I have one more. This is more of a simple example. This is a standard first order RLC circuit, and it does an impedance calculation. So the point here is that we're defining all of these things with units, okay, the frequency, the resistor, 8 ohms, the capacitor, the inductor. It's a first order RLC, so one resistor, 1 capacitor, 1 inductor. The angular frequency is 2 pi f. The reactance for the inductor, the reactance for the capacitor, and the low frequency and high frequency impedances, okay, in ohms. And you can see these are complex numbers, so the math engine supports complex numbers as well. And then this is the total impedance equation, and the total impedance is this value here. And then you can extract the real and imaginary components of it if you want. So the next thing we're going to do is use a Mathcad program to loop over all of the frequencies that we want to process and calculate the impedances. Okay, so there's the program. And the nice thing about programming in Mathcad is all of your natural math notation goes into the program. So when you're programming in Mathcad, you're still seeing the equations at face value for what they are. You're not seeing traditional programming languages, parentheses and characters, and you're seeing the actual math equations inside the program. So when it comes to verifying and validating something, it's very easy. Everything is at face value. Everything is transparent. And then this is the impedance plot. So we have the low frequency. Remember, we talked about multiple traces. We have the low frequency impedance here in blue. We have the high frequency contribution in black. And then we have the total impedance here in red. And that line, you know, we probably want to get a little bit more granular so that we can see how that is constructed. But there's the plot, the impedance plot. So I know we have about 5 minutes left until the end of the hour. I think I'm just going to recap very quickly here, and then we'll open it up to Q&A. So the thing to remember is that Mathcad is an engineering application designed for engineers. So with that in mind, it's much more easy to do your engineering work in Mathcad because it's a whiteboard interface, live math engine. You can take notes. You can document your assumptions, your decisions as you're doing your work. You don't have to go to a separate application. You don't have to take notes on a piece of paper or a napkin. You can take notes right in the application, document your assumptions, your decisions, your thoughts as you're doing your work, integrate your math, your text, your graphics, and then you have a reusable document that can be reused again and again and again. That'll save you a lot of time and a lot of headaches down the road and really change the way that you do engineering design work. So I want to thank Nav Edge for having me today, for giving me the opportunity to present to you. Thank you very, very much, Nav Edge, and thank you all for attending. And I'm going to hand it back over to you, Barbara, to handle any Q&A that might have come in.
Yes, thank you, Angie. That was very impressive. It's the first time I see Mathcad in action, and wow, I can see the universal application for engineering. Yeah, that's fantastic. We don't have any question at the moment, so I'm going to leave a few minutes. I'm going to leave it open to see if somebody, can speak up or raise their hand. But I also want to remind everybody that now and up till June 23rd, we have a special on Mathcad and a few other products. And so the promo is we have Mathcad, a line of Mathcad products at 35% off. So there is no better time to get Mathcad. And after this demo, I know I want one. So here's a couple of questions, Angie. Can I create my own units? The built-in units for energy in the customary English system don't include those I generally use.
Okay, yep, that is a very good question, and you can create your own units. So let me the short answer is yes, you can. And I'll do one very quickly. So if we go over here, back over here, I know you're talking about energy units. I'm going to show you how to do this with flow rate. So here, flow rate, we have gallons per minute, million gallons per day. There's a big gap there between gallons per minute and million gallons per day. There's no gallons per hour, for example. So the same would apply to you for energy if you want to create your own energy unit. So now here I'm going to say, let's define gallons per hour. So GPH, I'm going to define it, that's going to be 1 gallon per 1 hour. And now we can just click on this. What you have to do is go up here and say label this as a unit. And now that's a unit. And now we can use that 4.4 GPHs plus 23, and we could just say GPMs. Okay, and so now because gallons per hour is a new unit that we made, we can convert it to gallons per hour. So that's how you do it. That's how you would do that. And then I would put this in a template. Remember I talked about templates. I would put that in a template. That way it's there and it's available for you in every Mathcad worksheet that you create. Next question.
Pretty cool. No, there's no other questions, but let's see. We can wait another few seconds. That was very cool, Angie.
Yeah, it's very flexible.
I don't see any other questions, so I think I'm gonna take the screen back on to myself. Let's see, and see if you can see my screen. And I want to thank everybody for attending this webinar. And I also want to remind you that if you want to take advantage of the amazing promotion going on right now, you better hurry because you have till July 23rd to get Mathcad at 35% off. So I don't know how many of these offer we'll get in the next few months, so check it out. And also I want to remind everybody to follow us on our blog, Google+, or Twitter. And I want to thank you again for joining us today and remind you that this webinar is being recorded, and if you want to rewatch it, just go over on the Novage YouTube or Vimeo channels, and there's plenty of webinars. This is only the number 200th webinar, so you can have fun all day. Thank you so much, Anji, for introducing Mathcad to us, and I'm very excited for this partnership between Novage and PTC. So hopefully we'll work together again and demo again other features of this or other products. Thank you so much, Anji, and yes, visit Novage, novage.com. Bye-bye.